Welcome, everyone, to the virtual workshop on ocean connectivity and exchange across the Antarctic Peninsula. We're very excited that you are here. My name is Carlos Moffat. I'm an associate professor of physical oceanography at the University of Delaware in the US. Before I get going, I want to acknowledge my co-organizers, Tiago Dotto from NOC in the UK, Andrea Piñones from the Universidad Austral in Chile, Marilyn Youngs from the University of Maryland in the US as well, and Kate Hendry from the British Antarctic Survey. I also want to thank Julia Bach, who's at the Southern Ocean Observing System main office, who was incredibly helpful in getting us organized for the workshop. Speaking of SOOS, of the Southern Ocean Observing System, if you are somewhat new to Southern Ocean or Antarctic work, you might not know too much about SOOS. I encourage you to go to the website. Lots of exciting activities and work under the umbrella of SOOS. This includes coordination for fieldwork, enhancing capabilities for fieldwork, all kinds of interesting work groups, and other activities that you might be interested in. I'm going to also recommend that if you're interested in the Antarctic Peninsula or the Scotia Arc, that you sign up for updates for the West Antarctic Peninsula and the Scotia Arc Working Group that I co-chair with Juan Hofer from the University of Valparaiso. These slides will be available later if you want to scan those codes. SOOS also provides opportunities for leadership or for you to contribute to this community. In fact, our neighbors, the Amundsen and Bellinghausen sector ABS regional working group is now looking for new members. And so if you do work that is relevant to that region of Antarctica, please consider signing up for that working group. I think applications are due next week. All right. And so, as you might imagine, we have people from all over who sign up for this workshop. This is a little map of all the people who sign up. Very exciting to see people from all over the world kind of speaks of the nature of Antarctic work. And so that made the scheduling a little challenging. And so we understand that you might not be able to attend every session, but we'll be able to put most of the talks available online. So we'll send a link for that later. For now, this is our schedule for today. Each day is going to work more or less the same. We are going to have 3 to 4 talks. On the first 2 days, we have a series of lightning talks, quite short, 1 or 2 minutes, because we know we can't really cover all the exciting work that is being done in this region or in these topics. So we want to give people the opportunity to tell us about all the amazing research that people are doing. And then we're going to have a discussion at the end of each session around a series of questions or other questions that the community might bring up as we talk. We are going to ask you to hold on to your questions or post them on the Q&A window on Zoom for the speakers. So we'll go through the talks and the lightning talks first, and then we'll have a general discussion about all of the day's talks, okay? And then this is a list of the talks that we have for today, for later today. Hopefully people have had the opportunity to look at the schedule, but I'll just call people up as we get to that point. So before we give the microphone to Sergio to tell us about climate and change and variability and extremes in the Antarctic Peninsula, I wanted to tell you a few words about the motivation, the physical setting in the ocean for the workshop. Here I go. So perhaps the simplest way to think about what motivated us to set up this workshop is this figure from a very nice paper by Andy Thompson in 2018 that shows the properties of bottom water around Antarctica. This is in the upper right here, temperature and salinity. And given that and the forcings on ocean properties along the shelves of Antarctica, they were able to classify broad regions of the Antarctic coastal regions into warm, fresh, and dense shelves. And if you do that, I think it's fairly clear that around the Antarctic Peninsula, we have this really stark contrast in ocean properties on either side of the peninsula. One on the west, influenced by warm water accessing the shelf from along the Peninsula Sea, which is typical of West Antarctica, and then on the Weddell Sea side, very cold water, water mass formation, so very different properties and regimes on either side. And this broad distribution of properties has very important impacts. Number one, I think, is the distribution of continental ice loss around Antarctica. This is from a paper by Rignaud in 2013. And the details are not super important in this, but what matters is the size of these circles that you see around the continent represent the rate of continental ice loss from calving in the dashed lines and melt in the solid. So the bigger the circle, the larger is the ice loss. And of course, West Antarctica, this region that, because the ocean drives so much of the ice loss, the West Antarctica is a hotspot for ice loss from Antarctica, and the Antarctic Peninsula, the West Antarctic Peninsula is one of those hotspots. But this figure that I show you here on the right, you can think of it as a kind of a climatology of temperature. But if you think about change over time, we also see that the rates of change in these two distinct regions of either side of the peninsula are also different. So we've seen significant warming along the WAP, and this is from a paper in 2014, looking at, again, the evolution of bottom water properties on the shelf. Well, at the time anyway, the bottom properties in the Weddell were either not changing very fast or actually cooling. And on the right is the uplift of this very important water mass around Antarctica, circumpolar deep water, which is a source of heat for the melting of that continental ice loss, also showing very distinct rates of vertical motion over time. If we look at other key processes around Antarctica, again, just to highlight how important regional variability is around the continent. This is the evolution of the sea ice season duration from the first 30 years of satellite data around the continent. And reds indicate that the sea ice season is getting shorter. Blues indicate that the sea ice season is getting longer. And again, we see very stark contrast on either side of the peninsula, where the Bellinghausen Sea side, the WAP side, really showing one of the largest rates of shortening of the sea ice season by around 3 months, while on the Weddell Sea side, mostly we see lengthening or not very much change at all. And so these rates, of course, have changed. Recently, we've seen a big change in sea ice in Antarctica, but just this is to illustrate how distinct these two regions are. If we kind of zoom in now and think about what's happening in the smaller scale of the peninsula, it's really hard to give credit to all the exhaustive work, all the great work that has been done in this region. You'll hear more about this later on during the workshop, but I just want to highlight here some nice studies by Thompson and Professor Haywood, looking at the circulation around the tip of the peninsula and on that side of the Weddell Sea. And on the upper left side, you have the deployment of surface drifters that allow them to really understand the surface circulation quite nicely. And on the bottom right, there's a nice kind of cartoon of some conclusions of the understanding of the circulation from the Weddell Sea and crossing over to the West Antarctic Peninsula. And so key features of the circulation in this region are the coastal current that is driven by meltwater and coastal winds. I just want to remind you that coastal winds in general are going anti-clockwise around Antarctica. And of course, all the meltwater that is being delivered to the shelf. Along the shelf break, the Antarctic slope front, and farther offshore, the Weddell front. And this coastal circulation that is moving around the tip of the peninsula and entering this key region, Bransfield Strait, then takes the cold water that is being, that cold water from the Weddell Sea and flooding the WAP. And I would make the case that Bransfield Strait is the true boundary between the Weddell Sea and the Bellinghausen Sea. So now, if we look at what's happening on the other side of the peninsula, some of the same features of the circulation that we see on the Weddell. So we do still have a coastal current. You'll notice that this is not drawn as a continuous circulation along the coast because we don't fully know. We don't actually think so, but we're still kind of figuring that out. Offshore, the Antarctic circumpolar current carrying circumpolar deep water, which has, again, easy access to the shelf. And so this shelf is much warmer than the Weddell Sea. And the combination of these two, of the Weddell Sea influence and the Bellinghausen influence on the shelf properties of circulation results in one of the strongest gradients of ocean properties anywhere in Antarctica, where we have that cold Weddell Sea water to the north in Bransfield Strait, and then that warm water from the Bellinghausen Sea to the south. And this is, simplification of what's happening, of course. We also have very strong gradients in the cross-shelf direction as Bellinghausen seawater enters into Bransfield Strait along the South Shetlands and circulates around the islands. So this is a region with very strong, very sharp frontal regions where we think that a longshore exchange is actually quite significant and not well understood. And as is the case for the Antarctica as a whole, these gradients in ocean properties have a strong influence on ice loss patterns from the continent. So this is a paper from Cook et al. In 2016, showing that glaciers in that southern region flooded by Bellinghausen Sea water, warm water, CDW, are melting faster than those in the Bransfield Strait region, which are much more heavily influenced by the Weddell Sea. And so I think many of us have an interest in understanding how these two regions are interacting. What are the relevant processes that control that interaction? And to what degree do we see remote impacts of these processes elsewhere in Antarctica? I'll give you a few examples of that in a second. So one of the things I often look at as an observationalist is how are models doing in these regions? And you often see, especially when you look at circumpolar models, that they tend to have kind of cold anomalies along the WAP, so cold biases along the WAP. And that's just kind of, I think, a reflection of how challenging it can be to represent these processes of exchange that are happening around the peninsula in this coarser model. So I think it's an interesting challenge, given how important getting the temperature right is to things like melting rates. And so, and the other bit of motivation that I think is important is how this different regions of Antarctica might be influencing each other. And I'll give you three examples very quickly just to finish up here. First is a paper from 2017. These are all modern papers showing that anomalies of wind along East Antarctica resulted in the generation of coastal waves that propagate around the continent in a kind of anti-clockwise direction and generated anomalies of temperature along the WAP. Another one, a more recent paper by Marflexis et al. Showed that anomalies of meltwater along the WAP now propagated as a coastal current downstream into the Amundsen Sea and generated anomalies in melting rate in ice shelves, again, in this to the west of the WAP. And the third example is a paper by Adele Morrison that showed that modulation of Weddell Sea deep water production was having an impact on, again, temperature anomalies on the WAP, suggesting that there's a stronger connection than we might have thought between this region and the WAP, much farther than Bransfield Strait, I should point out. And so the motivation of the workshop is this, is to try to understand more about how in both regional scales and larger scales around Antarctica, these two regions of Antarctica are interacting with each other. How does this pattern of circulation that we see here is impacting things like real fisheries, marine productivity, carbon, and nutrient cycling. We also want to try to identify what observational modeling tools we need to address these questions. So you'll hear about advances in modeling and observational techniques. And because this is a SOOS activity, also what barriers to collaboration exist that we should address as a community. So again, this is a very quick overview of what made us do this. So now we're going to move on to hearing from our speakers for today.